The previous lecture modeled the diode behavior as an exponential function in terms of the physical characteristics of the diode, as well as the temperature and voltage across the diode. Although this might accurately model the behavior of the diode, it doesn't really provide a practical set of equations to use when designing with diodes. For this reason, the piecewise linear model is often used to model the diode behavior, which makes it easier to design with the diode. The piecewise linear model attempts to model the exponential behavior of the diode using a simple linear model which is easy to work with. To build a piecewise linear model, the diode is modeled as an ideal diode, some built-in potential E0, as well as some finite resistance R0. These elements are all in series, so the voltage function across the diode as a function of the current through the diode is simply the internal voltage and the current multiplied by the series resistance. This holds true for a forward voltage which is larger than the on voltage of the diode. If this piecewise linear model were to be plotted on a set of axes which modeled the current and the voltage of the diode, it would look like this. No current flowing until the forward voltage is larger than the turn-on voltage of the diode, and then the current would increase in a linear manner with the gain or gradient of the current given by R0. Depending on the design goals, there are two ways to improve this piecewise linear model. One is to expand the model to include the breakdown voltage. The other is to simplify it even further, where the diode's behavior will simply be to turn on at the forward voltage of the diode, in which case the curve will look something like this, with current simply increasing to whatever is required at the turn-on voltage. For a model which more closely approximates the exponential function, the diode can be modeled to include the breakdown voltage as well as the slope of the current as it approaches breakdown. To do this, the sort of idealized piecewise linear model is taken as the base model. It still contains R0, the turn-on voltage E0, but also includes two additional parallel branches, both consisting of ideal diodes, but reverse biased in relation to the main ideal diode. These two additional branches model the behavior of the diode when the voltage across the diode terminals, the anode and the cathode, is less than 0. The breakdown voltage is modeled as a separate voltage source which is opposed to the internal forward voltage of the diode, and the slope of the current as the diode current approaches breakdown is modeled by a resistor RL. In much the same way as the forward voltage would exceed the turn-on voltage of the diode, it would conduct current in the forward bias region. When the diode starts to enter breakdown, once the breakdown voltage is overcome, then the ideal diode in this branch will cease to conduct and current will start to flow through this branch here, which models the behavior during breakdown, where the reverse current to the diode actually starts to flow at the breakdown voltage. The piecewise linear model from the previous drawing is good enough for hand designs and for analyzing circuits, but in order to correctly simulate the diode, a more complex or more comprehensive model is required. The model shown here is a physics-based diode model, which is often used to simulate diode behavior, especially when using a package like SPICE to simulate the diode. In this model, instead of devising a piecewise linear model which approximates the behavior of the diode, the device physics are instead approximated mathematically. This model consists of a series resistor between the anode and the cathode, a current source, as well as a variable capacitance, which represents the capacitance across the junction of the p-n junction in the diode. Despite all this mathematics, the model is actually not that complex. This current source, which represents the current for the diode, has two components. It has the forward current component as well as the breakdown current component. The forward current component is given by the saturation current modeled by the familiar exponential behavior seen from a previous lecture. The saturation current is once again defined in terms of device physics such as the dopant concentration, the electric charge, and the area of the junction. I subscript V as a function of voltage represents the reverse breakdown current that flows through the diode when breakdown has occurred. The total current through the diode will then be the sum of the forward current and the reverse bias current. In a similar fashion to the current, which consisted of a current in forward and reverse bias, so the capacitance is represented by a capacitance under forward and reverse bias conditions. The junction capacitance is present under reverse bias conditions, and the transit capacitance is the dominant capacitance under forward bias conditions. The transit capacitance is a function of the carrier transit time, T subscript T, as well as the change in current through the diode as the voltage across the terminals changes. Depending on the voltage across the terminals of the diode, the junction capacitance will be expressed in one of two ways. In both cases, the junction capacitance is expressed in terms of the zero junction capacitance, which is the capacitance under zero bias, the voltage, and M, which is a coefficient known as the grading coefficient and is a process parameter determined by the doping of the N and P regions. This zero bias junction capacitance can, however, be derived from the doping profile at the PN junction. This diagram is borrowed from the reference material, and it shows the doping profile for the N region and for the P region. Of importance is the behavior of the fields and concentrations in the space charge layer, which runs the boundary over here of all the graphs.